this is the beam line. Today, you don't have to worry about the beam, because first we have safety issues here, but also today the ring is shut down. So everything is okay, so you can go around, take picture if you want. So this is the SAX beam line. You know what SAX stands for, is small angle X-ray scattering. So the word is scattering. It's the same that in diffraction, that we observe a phenomenon that is related to how the incoming beam changes the trajectory due to electrons. So this is the same principle that as X-ray diffraction. But here, well, there's subtle differences that I will tell you later. But the principle is the same. If you do or did diffraction in the past, the principle, the physics behind is the same. So we have several parts. This is the experimental hatch. As the other beam that you want, in the beginning we have a shutter that it's a very big block that block the beam. And so when we have beam or electrons going around the ring, you can safely enter here. A single photon is here, so you don't have to be worried about it. When you place your sample, now after a protocol, you go out, you follow some rules that doesn't matter now, and then you can open the shutter and then receive or illuminate your sample, take measurements. So this sample, this beamline has several parts. You can go here. If someone, I don't know, well, so a monochromatic beam came from the ring. Here is in a diffraction experiment, it's a monochromatic beam that elastically scatter from the sample. So there's no loss in the energy. So the incoming beam have an energy, and what we measure is the same energy that the incoming beam. So here you can control from the hatch which is the size of the beam. It will depend on what kind of experiment you want to do. It's not the same if you do an experiment by grazing incidence or transmission. And you place the sample here. I will show you later a few sample holders and what we can do. Or as you see, this is a very huge sample holder. So you can play here, as Eduardo told you during his talk, 3D printer. So this space is very huge, and this table can weigh up to 70 kilos, more or less. So you can place something very big here. We don't have to worry. But if you do a transmission experiment, the usually thickness of the sample is about 1 millimeter, 2 millimeters. So it doesn't matter what you place here, but the thickness of the optical path, it will depend on the material, but more or less 1 to 2 millimeters. If bigger, you lose all of the beam. So you can see here a detector and another one on the final of this tube. Which is the difference between both is the angle we can measure. Here we can do both a diffraction experiment and a small angle scattering experiment, both at the same time, because with this one we have a detector very close to the sample, so we can measure at wide angles. This stands for watts detector, watts W for wide, and another detector there for small. So what we can control is the distance between the sample and the detector. If you see now, it's a very short tube, but the hatch is very long. So we can play up to 7 meters long, the distance between the sample and the detector. Why I do this? It will depend on the sample, because in this case, this is a technique that with low spatial resolution. We can measure things in the nanoscale range. So depending on the sample, we choose the better geometry. So this is related to an experimental way of doing a Fourier transform. So if you know Fourier transform, we operate in the reciprocal space. So if you have a very high spatial frequency, you have to measure at higher angles. If you have lower spatial frequencies, like a big object, you measure at lower angles. So if your object is bigger, you have to put further away the detector. So this is the main principle. How far away? It will depend on the sample and the incoming wave. I will show you later on the screen only one equation, but just to understand what we're doing. So we can solve here things that in the diffraction regime of sub-nanometer to 150 nanometers long, depending on polydispersity or the thing. So is the sample very high polydispersity, obviously you can solve a lot. So you can take pictures without problem. So you have a question for this part. So here we can do grazing incidence experiments or transmission. In transmission, we can control temperature, the atmosphere with gases, and we can measure powders, liquids, shells, well, films, because grazing incidence for films. So I don't know which kind of materials are you interested in, but if you work with proteins, we can measure proteins in solution.
And you do it in diamond Andrew cells?
Time resolves? Yeah, depending on.
Diamond Andrew cells. Diamond Andrew cells. The high pressure.
No, not now. No, in this beamline, because when I said for protein here is more like for protein solution.
Sure.
So maybe you can solve the structure by single crystal, and you say, okay, this protein is the same in solution as in the crystal.
Yeah,
so
I understand, but I'm asking about
we don't have now a high pressure cell for this kind of experiment, but maybe in the future we can think about it. I think it's more interesting in solid, the high pressure, than in liquids, but we don't have now.
Actually, I've got another question. So this whole tube can move, right?
Yes.
So if you put it further, does the air influence the signal? Because if it's further, the
you lose signal because each pixel receives less photons.
Yes.
But the flux is quite high, so just for a single measurement, you usually do 1 second to 2 or a fraction of a second, so it doesn't matter. What is more important is the radiation damage. So in that case, for proteins or this kind of material, most, that if you illuminate the sample for quite a long, is just a second, maybe you change the structure entirely. So in that case, it doesn't matter the saturation or the level of noise that you have, but it's more important the radiation, the damage of the sample due to the radiation. So But yes, when you go further, each area or each pixel receives less photons. But it's not an issue here, it's more an issue in laboratory equipment, because here the flux is very high. So let's go inside.
Just take a picture real quick.
Yeah, sure.
Question because we are also preparing the cycling line.
Oh, yeah, sure.
Yeah, so probably I will catch you later.
Oops,
And
sorry.
we can
Yeah, sure.
discuss a little bit.
Whatever you want. So,
Te vas a poner ahí, ¿no?
acá y allá. So, what we are measuring, think about this. We have a sample, yes, that the principle that we observe scattering is due to difference in, yes, there's a chair there. We saw difference in the and in the scattering construct that is due to electron density. So the interaction of the X-ray with matter is through electrons. So if you have a material with some electron density and a medium with another one, now you have this difference, and in this difference you observe scattering. So it's the same for diffraction, but in that case the difference is because of atoms. So when you see a very small scale, if you make you very tiny and you can observe the difference in the atoms, this inhomogeneity is due to here we have an atom, here another, and here another. In this technique, now we have bigger material, so a nanoparticle, for example, nanoparticle can be a protein. We saw as an homogeneous object with an average electron density. So we observe here, and we change the direction of the beam due to these homogeneities. And we can place the detector here and here. And this is how it is. So depending on the detector, this is the width or the area of the detector. If we place it very close to the sample, we can achieve larger angles. So this is a diffraction experiment. So when you go to your beamline there, you place the detector, it's a very big detector, and you place close to the sample. If you put this detector further, now the solid angle will be smaller, and you can solve small angle but with high resolution in angle, because the pixel of the detector is the same. So you play further. It's like when you see people here are all big, but from the plane or helicopter, I never went to a helicopter, but they're very tiny. So it is the same. So in that case, if you did a diffraction experiment in the past, you see something like the count intensity in function of something called 2 theta, that is the diffraction angle. And this is the diffraction angle. But for us, or for the people that work also in diffraction but in synchrotron instead of laboratory equipment, we are interested in the diffraction vector Q. This diffraction vector is related, or the module is related with the incoming wavelength energy and the scattering angle. So usually when you do a SAC experiment, you don't see 2 theta, you see Q. And this is better, in my opinion, variable, because when you see a diffraction pattern in 2 theta, you have to indicate to the reader the energy you're working. Because you change the source, you change the 2 theta. Here, you normalize by the energy. So if you observe a Sachs pattern with the X-ray source, regarding the incoming energy, or even a neutron source, for example, SUNS is neutrons, neutron, small angle scattering, the Q is the same. So if you see a peak or a shape of a nanoparticle in one experiment or the other, it doesn't matter the incoming energy. So depending on the dishomogeneity size, you will choose a geometry, or you place close to the sample holder or further away the detector. So it depends. So this is very important to know, because it's not the same if you come here and say, okay, I work with the chocolate factory, and you know for chocolate it depends on the polymorph of the fat, so the quality of the chocolate. Because if you see this white thing is called blooming, the one polymorph cause it and the other not, and is smell in your mouth and you are very happy. So it will depend on how it process the material with this info. Well, in that case, you have diffraction pattern around the 5 nanometers or something like that. So you place 5 nanometer for us is small. So you place the detector close. You come here and say, I have this material that has 100 nanometers of diameter, and I want to know the size distribution because I want to compare between this synthesis process to this one. Well, we place further. Or we change the energy, because sometimes you have, I don't know, iron in your sample, and if you use 8 keV, that is the source of copper, the iron have fluorescence, so it might change the result. So it would depend. So, question? What kind of sample we can measure? So we have here several sample holders. Is not all of them, as you know. If you want to think a very crazy experiment, you can do it. So we can put here something like films, for example, a polymer for packaging. For proteins, usually you use something like that one with capillaries. The problem with capillaries is that not all the capillaries are the same. They have like a 20% difference in the diameter. So sometimes to extract the background is quite complicated, and they're quite expensive. So 25 capillaries cost more than 100 euros. Just two. So, and they're very delicate. So, but well, you can use it. There's another options for this kind of thing. This is more common for biological beamline, that you have a capillary and something that put your sample inside with the flow and this kind of thing. But well, not only proteins. You can observe a lot of fluids for nanoparticles, micelles, polymers in solution, this kind of thing. Also, well, if you have powders and do a simple diffraction experiment, a powder diffraction experiment, you can put it here. You can control temperature. I know Eduardo showed you a very nice experiment with tubulins. They orient some tubulins that work for the cells splitting. I don't know if you remember that he showed a very nice lines there. Well, they do this experiment with this sample holder that is like a rheometer that is moving with the motor, the plate, and apply a force to the sample and orientate it. So in that case, if you have something that like this one, that imagine that is higher in this direction, but not in this one, you have a diffraction pattern here because it's ordered. So if you can orientate, you can see in this direction the diffraction due to these lines, and in that direction to that one. So after orientation, you can observe, okay, this diffraction corresponds to, I don't know, this folding or another one, depending on what are you doing. And lastly, but not least, you can do grazing incidence experiment. You have to be very careful because sometimes students are very confused after this kind of courses because this is a very small angle technique. This the region we are measuring. But for grazing incidence, grazing is small angle, but incidence. So we place at very small angle the film, but we measure also a very small angle scattering. So you can do this kind of thing also for diffraction. So it's also a grazing incidence, but you measure diffraction. So just to this kind of sample holder, you can control the temperature or place gases. If someone works with catalysis or this kind of thing, this is very nice to do diffraction experiment or grazing incidence with a certain atmosphere or temperature. This kind of sample holder can go to 600 degrees more or less, and this one for capillaries 300 more or less, but for soft matter 300 is a lot. So, well, question about the sample holder, or what kind of experiment you want to do?
I've got a question. Are you doing these sample holders by yourselves or you're...
Yes, all are doing by ourselves, even this one. Well, the one, well, she's there, but we have there a sample holder that is for stretching. This is a commercial one. If you have a polymer for packaging or something like that, you can do experiment while stretching. But yes, it's a mixture. This one is a commercial one, this part, but it depends. Few times we talk with the users and they bring their own equipment or house-made equipment depending on the scene. But yes.
Okay.
So finally, I will show you. Today is machine day, so we don't have any beam. So I will show you what we do with the data, and simulations have to try to understand what we are doing. But from here to understand SACs is a very long pathway. So no, thank you. So first thing first. You as user came here and you take measurements and you have data, but in order to convert this data to angle or Q, you have to calibrate the equipment. So this is the first thing. Which is calibration is measuring the distance between the sample holder and the detector, and where is the beam are hitting the detector. With this, you can say, okay, which is the angle? Is the distance between here and here? We have an angle, another, just a trigonometric equation. So this part is a beam stopper. You know which is a beam stopper? Something that stops the beam. And why we use this kind of thing? For two reasons. First one, to not burn the detector, first of all. And the second is not to saturate it. Even if you don't break the detector, you saturate it because the transmitted beam is too high in intensity. And it's the same analogy that maybe we are walking around the mountain and someone say, oh, look at the birds, are very nice. And you say, but it's the sun, and you see nothing, so you put your beam stop, and now you can see the birds. It's the same analogy. And we use here a substance that we know the diffraction pattern, so we know exactly at which angle appears the diffraction. So this is known. What we don't know is the distance. So we calibrate with this. This is silver beigenate. That is a fat acid with silver. And it's a lamellar structure. So in every lamellar structure, all the diffraction periods are equidistant. So this is the first one. Equidistantly is the second order. Equidistantly the third order. So using this, we can. This is just a software, a free software, but it doesn't matter. The software itself is just to show you what we do. I indicate the incoming energy, which kind of calibration we use. Here, this software, what is nice that you can indicate the detector you have, because here you can see we have several dead parts, because detectors in this case are modular detectors. So you can buy one module or a lot. So depending on the size or the area you want is the number of modules. But between modules there's a dead area that you don't count anything. So you have to mask it. Well, so this software already know. So after that, for every experiment, you have to mask what you don't want. First is the dead area, and second one, for example, is the beam stopper, because here you have some intensity, but here none. So when you analyze the data, if you don't mask this region, it's all messed up. Because in this case, as you see, is everything isotropic, because you have all the orientation in the same sample. So this 2D pattern is redundant. So what we do, we integrate in an azimuthal way to go through a 2D problem to a 1D problem. Thus, after that, we select the peaks. You say this is the first order, second, third, and then we calibrate, and well, it's just a fitting. And you say, okay, it's, in this case, particular, 3.6 meters away from the sample. So now you have the distance, you have the center of the beam, and with that you have the angle. Yeah. And you can integrate and go through a 2D problem to 1D. Only if you have isotropic samples. For example, protein in solution, nanoparticles in solution, powders in general. But if you have a polymer by stretching or a surface, now it's intrinsically anisotropic. And for example, if you have something like, well, you know, this one, that is a simulation for something like that. If you have the surface with cordial particles on the top, you will see something like that. something like that. Obviously, this is a simulation. It's too nice. Never, the life is never like this, but it's anisotropic, so you have to be careful. And finally, the most problem with SACs in general, and this is experience talking, that doing an experiment is quite easy. You come here, happy, put the sample, press enter, and then you have a lot of data. Imagine that less than a second per frame. So sometimes people go to their home with thousands of data. The problem is what they do after. So this is a problem because what you will see, but the data is not well defined. For example, in particles in solution, it's not like a diffraction pattern that you say, okay, I have here a peak, another, it's a cubic cell, I'm happy. This is quite harder because all the samples are alike. So obtain information from this is not as easy. Nothing is easy in life, but in this case, you have infinite solution for the same problem. So you have to put a lot of inputs, previous knowledge of the sample to solve this. So for example, nanoparticles in solution. Someone came and say, okay, I have a synthesis. I want to know the average size and this particle distribution. So this kind of sample, for example, gold nanoparticle, is the dream of a physicist because the solution is a sphere with with nothing more than a sphere in vacuum. So this is the dream. So in that case, we will see the looks like. I will put something here. Just a few parameters, don't worry about it. So this is what you can see. This is the shape of a single sphere vacuum. So here, first thing first, we always plot in 1 or 2 axes in log scale, because if you see, we have like 4 to 6 order of magnitude from the first point to the last one. So if you plot in linear scale, you see something that decays fast, and that's it. And then from here, you can see is related with the average size. What happens if the particle is larger? What will happen with this pattern? To the lower angles. So if we place here, now we have 50 nanometer, 80, this thing will shift to. And the other thing, if we have a collection of sizes, so a distribution of sizes, now we have to sum all of these contributions. So what we will see is that this oscillation will be smoother. So if we place polydispersity, for example, 10%, now this is smoother. So if you have spherical nanoparticles in solution, the dream, without quite diluted, because the other problem, if you are quite concentrated, the average distance between particles is in the same size of the particle, so you have an structure. So in the case of diluted particles, from this loss of oscillation, you can obtain the distribution of particles in solution. So well, this is more or less what we can do. Obviously, there's a lot of problem. You have, it's not the same a polymer in solution than a polymer in a bulk. The problem is huge difference. So it will depend. But the most important thing is that you have to know a lot of information of your system before go to SACS and obtain information from SACS, because you can have a, I don't know, a banana-shaped particle that give you, and you can put a lot of sphere until you fit all the data. Now, you know, if you have 100 of parameters, you can model an elephant. So you have to be very careful and know a lot. What kind of experiment you can do here? For example, time resolve. You can do, for example, synthesis in situ and go from the when particle burn to the growth, or melting, change of phases. Well, a lot. Or for example, you have a doll, and the doll have an arm, and all the kids cry because it's always broke in this part, and they say, why? It's because it's thinner, or there's another reason. Well, sometimes for the manufacturer, you see an orientation of the polymer here and another here, and where they glue, it's weaker. So you can solve a lot of problems, but you have to know the problem before come here. Questions?
I have a question. What's the liquid in that tested? Next one.
I don't know.
The red one.
Here?
No, the liquid. It's the water or?
Here?
Yeah.
Ethanol.
Oh, okay.
Yeah, you can do things in solvents without problem. The main problem with solvent is in the wax region and diffraction, because solvent have a very strong peak, amorphous peak that sometimes hide everything. But without problem, you can do experiment in a lot of solvents. Here it's very nice because you can place a solvent here and do a solvent annealing with temperature. So, for example, if you have a sensor that is sensitive to the, I don't know, ethanol, you can place this sample holder at 40 degrees, for example. You know the vapor pressure, so you observe the changes on the surface due to the presence of ethanol in the vapor phase. Another question?